like a certain topic, I always am very upset if I go to someone new and they don't know me, and then they say, oh, what do you do? And I say, well, I'm a scientist. Oh, I hated physics in high school. Oh, I hate. That's like they will shut down and just have that kind of initial reaction, and so I would really like to be able to
speak up, I can hear
take away from this experience. How was I able to communicate an idea, and they really took something from it. They really, translated it into their own understanding, and then when I see what they created, it had meaning, and it wasn't just a lost, we weren't able to at some point, I guess. I don't know.
I guess requires effectively analogies.
Right, yeah.
Because it's sort of to bring it down to something that has nothing to do with it in reality, but close enough to get the message.
Even communicating scientific results to other scientists,
right?
Even in the same field. I mean, some people are better at it than others, but there are some people who are just terrible at it. And I think, we could all improve one way or another. And this is really an important part of the whole scientific process, in that if you find something, you want other people to understand what you're doing. Your results might all be correct and this and that, but in some sense, if other people can't figure out what you've done or what you're doing, it's not nearly as useful as it's meant to be. I mean, science is really a big collaborative community thing, and it works best when many people are able to get involved, even in a very specific scientific subject. And part of that is just communicating even within your field.
Right. Or, and also having, I think another aspect of this is like the creativity aspect. I think sometimes physicists will get kind of stuck in, well, this is the procedure, this is the way it's done, and maybe sort of that thinking outside the box. I mean, if someone has a new concept in the field, I think a lot of people, you as a physicist, I'd want to, make sure that it's verified, or, I think we're always excited to try something new, and, but how do you use that creativity in your own work? Like, if I just have a predefined procedure for how to do it, I'm more likely to I want to make sure I get my work done. I don't know how to bring creativity into my own work if I have
So how is it even possible to capture what the creative process is as a process? And does that actually look different for a scientist and an artist?
This is one question I have too.
And I have no idea if
How do you make a decision what to research? There must be urgency or like a kind of intuition you have that this might be getting somewhere, and then you apply all the different methodologies and working in a scientific way, or is it? I'm wondering about how where do you what's your desire?
Well, often it starts with sort of seeing there's I often describe it as folding the possible with the interesting. I mean, there's big questions out there, right? And so you may want to contribute to a big question that may interest you yourself, and potentially you have actually learned the tools to do so. You become a theoretical physicist or an experimentalist in a certain area, and you think, okay, how do I apply what I've learned and the tools I have available either in the lab, and can apply that to that question, or which question can I actually put? And so you sort of try to figure out, okay, what's the best way to apply those tools to a question that really should interest them to other people?
Artists. And I mean, I suppose I guess the same thing. How do you decide on what piece of art you want to do? I mean, some of it does come down to technical aspects. I'm able to do this, and I don't have the resources to make cookie-cutter brass sculpture or something. But I work in this medium, or this expertise to do this. But I guess in science, some of it is we're part of the community. A lot of it is related to being part of that community. I'm not sure if there's not really a simple answer.
Yeah, different people are also very differently motivated.
And your influence in this.
But I mean, typically we get very interested in something, we want to understand it better.
Yeah, I thought it was kind of interesting with the speaking about the cloudy spot. That's exactly what we're trying to avoid. Actually, is that right? You can have a place where it's sort of cloudy, then we're trying to really pin down what is actually happening there. And you really need a consensus of scientists. You know, if somebody says this is what they've measured, then someone else doesn't. You know, it's still undecided on that. As a community, we'll continue studying that until consensus is reached, and now that it's no longer a cloudy spot. So it's not really a region where we, you know, I guess in the artistic sense, there's you kind of thrive on that and you're able to go forward.
You have more tolerance.
Right, like you just really like the difference between having, you know, a unique result being artwork is good. But in science, you don't want your result to be the only person who's ever measured or is ever able to measure, because then, you know, it needs to be reproducible.
Just want to be the first.
Sure. Yes.
But its scientific reputation comes from being, in some ways, the first to understand something. That's what you get a lot of pleasure for yourself out, and then maybe recognition in the jobs and all that, and the prize, whatever.
But don't some of your ideas, like she mentioned in the model, they come from other people's ideas, and they're not random, they build. So in that model, the ideas, you get some ideas from other people.
Oh, absolutely. You completely you completely do that. I mean, there's sometimes the moment of inspiration is okay, but yeah, it's all in the context of what you've sort of been exposed to.
And sometimes it's taking, like you said, the tools. If you have a tool that's only been applied in one field, and you're able to transfer.
Me, it seems, you know, in my mind, it's like, oh, we can do whatever we want, but I'm sure that's not the truth, you know, that like you're also constrained by not just whatever medium you choose to work in, but also by, you know, sort of what we were talking about before, things that have come before, and, you know, maybe within a certain methodology that you choose.
But the artists create their own constraints.
Okay.
Like Joseph Cornell works with drawings, right? And I think, you know, let's say Heather's work is with drawing, so the constraint is it's always that material. And even if she wants to introduce color, she's limited by the colored pencil versus other elements. So the expectation isn't the same, but I think there is the constraint there. But I would still like to know what the scientist thinks creativity is more, in a more detailed sense. Like how do you think about that?
An experimenter has to, with a certain set of apparatus that's been built, and they can imagine what they could build if they have the money.
Infinite money.
And they then have the scientific question they're trying to answer, and so they got these elements, and they have to try to put them together.
That's the experimental thing.
I would say
That's my simplistic view. Tell me how it really works.
bang your head against the wall until something happens. I don't know, I'd say creativity is putting, in terms of science, I guess, would be putting together the elements that are available to you to find a solution or create something that is different than has been done before. I think it's the same also in other things. So you want to say, okay, I created this thing out of the blue, or I thought of this idea out of the blue, but really it's taking all these associations that already exist and finding a new association between them, finding a new link between them, thinking like, oh, I could use this thing to look at this, and that would tell me about this, or like, oh, I see this link between these two ideas, and I could combine those into a piece of art.
So that's where the power of multidisciplinarity comes in, because it brings in some perspective that you might not have thought of. In the theory world, it's quite similar. There's a set of problems that are the problems that everybody's supposed to be thinking about. So you can either have a brilliant idea and solve one of the problems, which is unlikely because many other smart people have been thinking about it ahead of you. So you need a twist, you need a new way of thinking about it, or you decide it's not exactly the right question that's being asked and you have to reshape the question in a way that gets you to the same place. But a front-on assault doesn't work too well. It's really hard to find a problem that you're smart enough to solve that nobody else has already done.
Well, same thing in art. It's the same thing in art, though. I mean, you know, so often I'm sure students feel that you have an idea, and then your instructor says to you, "Oh, so and so did that in 1953." And you're like, "Okay."
Very helpful instruction.
Well, but then what's the twist,
Yeah.
right? That's what we ask the student.
But when you were talking about putting together elements from sort of these, you have a toolbox of elements to put together, and then you're creatively trying to solve a problem. I feel that's the same thing that artists do, and in terms of maybe a certain set of concepts or a certain artistic technique proficiency that you're then bringing forward.
Right.
But you also are limited to a certain amount of efficiency in the artwork. Like you can't. It's the same as a physics problem. You can't explain the whole world. I mean, it would be lovely if you could, but then there's a certain package to it in a way too. So, yeah.
I was just going to ask, if you make a piece of art, do you also approach it like you're trying to answer a question? Do you also, because I always think of science in terms of like you're trying to answer a question and more questions come up and you try to answer those questions. But do you feel like art works the same way, that sort of like, or is it more like organic, like you come up with this concept and it goes here and it goes here and it goes here, or do you feel like you kind of, I guess people work in different ways, but do you sort of, I feel like there's a bottom up and a top down approach, right? And then, so one way one thing leads to another and you kind of come to an end that you weren't expecting, and then in another way, you know, you start from a concept or an idea that you have and you try to talk about it in some way.
Maybe I can jump in here. Is it safe to say that you work a lot with text and language to solve a problem?
We have a mathematical language, and that is.
What is that? What would you call that? If it's not text, what would you call that?
What would you call what?
Let's say those different. You say, if you ask if
Mathematics
artists.
is the language, but it's, at least for theorists, you don't start at the beginning like all the cartoons, you know, right on the blackboard. I mean, you know the answer, and you kind of arrange the math to get there. So it comes from flash of insight, and then you can't cheat in the math, but you can kind of build it up.
Right.
Get where you want to go.
So math is something.
Is that unfair?
I think it's, the cartoons give of maybe E equals MC squared.
It's too hard to just sit there and derive. You kind of know where you're going.
Okay, I'm asking this because of your question, because I think in arts we have a very much a perceptual approach to things. So it's not necessarily, depends on which area you work in. Of course, you can be a poet, but still, even if you work with language, you have an approach that is more about experiencing, and it addresses senses. Your sense is not so much just your rational mind with text and understanding, in the sense of my consciousness understands, or my mind understands something. I can basically receive an artwork and I have no words for that, because I receive it with my senses, with all of my senses.
So actually a physicist, you said, what would you do if you presented a drawing or something?
Yeah.
I mean, myself, I don't have the vocabulary to react coherently, so I would have to myself react emotionally.
Exactly. So
I like it or I hate it or something, but I mean, or I have some sort of reaction, but I don't have the vocabulary of a critic, and so I wouldn't even know how to describe it in words.
And it's not expected actually of anyone.
And actually words don't fit physics either, right? I mean, because math is the right language. So
it doesn't work?
So that's the question here. You're doing your best to put words on it, but it's not.
It's the question because
that's why physicists get along in every country, because they all speak the same language, and it's not their native language.
But in art, you can say the same thing. If you communicate on the level of images, you can talk with everyone basically. But here's the interesting point I find, because if you, let's say, accept to be part of a transformation process, you would probably accept to be exposed to an approach that is not, doesn't stem from reason and language and text, but from a perceptual context. you said emotions and images, associations, and the question is how could you come in there? How would that work for you? Or could this be something you can make as a resourceful for you?
I think it's actually interesting that it will work both ways for the artist and the physicist. If you pass things back and forth between artists and physicists, the artists will have sort of an incomplete picture of where the physics came from. Even, I mean, you can't teach you everything about neutrino oscillations. So you'll have sort of an incomplete picture, but then the physicist will also have an incomplete picture because we can't learn everything about where the art came from either and what's gone before, this like building up of both subjects. So we'll both have this sort of, I guess what you were calling the cloudy spot. It's not the same thing I think that you were talking about, but it's, sort of born of a sort of limited understanding of the other discipline. And I don't know if that's kind of the idea of the whole thing, is that you this like lack of understanding is the sort of idea of the whole passing things along, because then we will be forced to interpret this within a framework that's only our framework, and it's not an artistic framework, and so maybe we'll miss the cues to something that came before, maybe we'll miss a reference to a great artistic work that came before.
The noisy transmission.
Yeah, right. It's broken telephone, right? But I think we will have to respond from this sort of, we can try to sort of, but I expect that we'll respond more from the point of view of sort of this sort of our more sort of based in logic, and it will be hard to, I guess, because if you don't have a lot of practice at responding from the more perceptual point of view, then you always sort of fall back on the like, oh well, this is kind of similar to this part, and like maybe they're related, like.
But we've claimed that physics is creative, and therefore it's intuitive. And here these people are going to be coming forward with more. More creative input. Is that useful in any way, or we just go, oh, that's art?
Yeah, right.
I think that's an interesting question.
Where does intuition come in your way of working?
Well, how do you know the answer?
Static images.
Can I just ask you, going into behind the other question about the role of association and translations, because one of the aspects that we will be confronting is the translation challenges of moving from a physics concept into other forms of cultural responses. So even amongst yourselves, do you use analogy, metaphor sometimes to
All the
communicate?
time. Sure, of course. all the time. It's steady.
Yeah, well, especially for a presentation, right, or a talk.
Yeah, you're always using analogy and metaphor. Have to.
That's the main way that the Higgs boson is explained to the public.
Yeah, all kinds of stuff.
Yes.
The only way they understand it.
Because fundamentally, I mean, one of the big analogies we use all the time is things as particles, which you visualize as a little ball of some kind. And quantum mechanically, that is absolutely incorrect. There are no such things as, there's no little balls. In fact, in the language of quantum field theory, there's not even, all you have is little perturbations in a field, which has even less connection to little balls. But we do it all the time. When you draw a nucleus, you make everything look like a circle. The electrons are going around in orbits. You're just a mental picture.
Right,
now, in science, I mean, when you learn these things, we know in our gut that that's not the way it is. But it's a useful mnemonic. Yeah, because how else the hell, how else are you supposed to think about it? Right?
Yeah.
I mean, our brains, if you want to go to cognitive side, I mean, we can only visualize things like we're used to visualizing, balls and things and objects of shape and form. But in quantum mechanics, and especially the stuff he's doing, all of these diagrams, what's actually happening, if you could somehow take a photograph at that level, which you cannot, because light is many orders of magnitude bigger than what's happening here, it certainly will not look like that. right? That's not how it is.
Yeah,
But this is
yeah.
how you have to think about it
Yeah.
in order to try to make sense. So we're confined by our own evolution to thinking in certain ways, and so we always do that. We're always using methodology, not methodology, what was this?
Metaphor.
Metaphor, thank you.
What about when you're, sometimes you come up with some idea about how something works, so it's kind of in there, but is there ever, there's no logic about how it popped into your head? What about, is that a possibility as well?
Oh, sure, of course.
Yeah, so what is that, how do you describe that, or how does that happen, or why does it happen?
Why does it? It's usually when I step out of the shower.
Uh-huh.
Yeah, so I joke this all the time, like, I gotta think about this, I have to go have a shower. Because I don't know, you let your mind roam freely, you let your subconscious take over, and it's doing the calculations or whatever in the background, and I step out of the shower and I'm like, oh yeah, of course.
Yeah.
Maybe it could be just a title of a story, or it could be I solved the biggest problem in my thesis. It happened when I stepped out of the shower. Yeah, like the answer just popped into my head.
Do you know there's a book about this? You must know, what's his name? Csikszentmihalyi. He wrote a book called Flow. He's at MIT.
Yeah.
And so he wrote this book where he actually describes how often scientists work, and he talks about the shower as well. Like
Yeah,
the
for
idea,
sure.
there's something about doing something so that another part of your brain can relax, and it does the work without your willpower.
Exactly. Yeah, and we all do that. I mean, everybody who does this.
It only works if there's sort of an immersed in it for the while.
Yeah, you need a certain amount of background information to be able to do the effective.
Yeah.
Yeah.
I have a quick question.
Yeah.
What happened to your finger?
Well,
Oh, I did-
let's not get into that. You're the observer, so you have to stay in the
He was
observer role.
overthinking.
I dislocated my tendon.
Oh, okay, sorry.
Yeah.
So coming back to
Yeah.
that idea of the cloudy spot, or when we talk about that in art making, in that sense of the trying to exist in the spaces between known spaces and trying to work our way through that, how does that become a shared space for both of us? Or is that possible?
Yeah, maybe. I was thinking when I first heard that term, we don't want cloudy spots in physics.
Yeah.
No.
We're trying to remove the cloud.
We're trying to remove the cloud. We're trying to remove the fog. So if there's somebody saying, "Oh, I don't get what you're doing here," that's not a good thing. It's it's not a good thing. But however, it's not always a bad thing, because sometimes you could say, I'm thinking of the neutrino remember the faster than light neutrinos? So they're looking at it, and then there was some parts they're saying, well, wait a minute, what did you do about this? It's not clear. Maybe that's the solution to the problem. So what's clear to one person, sometimes I think this is clear. It's clear to me. I give it to Ewan. Ewan goes, what the hell is that? Is it this, that, or the other thing? And then I realize, oh, crap, yeah, you're right. I didn't think of it that way. So on the one hand, it's not a good thing. You're trying to be clear, right? Because we want to be as clear as we can in the passing on of the knowledge. You don't want misunderstanding. You don't want. However, it's also true that by actively trying to find the holes in the argument, like what I guess what you would call the cloudy spot, is where one can also find solutions. It's like, I didn't think of that. Like what says it turned out in the neutrino, there was a loose cable. Somebody said, hey, did you check to make sure all the cables were tight, because it affects how the signal rises from low voltage to high voltage.
Right.
And everybody, oh yeah, right, I guess that's, and then they checked and it turned out that to be the answer.
I think a lot of our cloudy spots, things, we're trying to solve those. So they are things that we know about the universe, we've measured, and we've discovered that we don't understand it. This question of what is dark matter. We know that there's something weird going on in the universe.
But we don't know what it is.
We don't know what it is. So that's our cloudy spot that we're then trying to clarify later.
Yeah.
So that's interesting, because that idea where you say you measure something, you get the measurement, but you don't understand it, what you're getting in a sense.
That happens. Yeah, and that happens. In some cases, it could be bad. Like, this isn't behaving as our Monte Carlo predicted, for example. So that's a bad thing because you can't, a lot of times you're looking for differences between expected behavior and unexpected behavior. And if you can't predict what the expected behavior is, that's a problem. However, it could also be an opportunity because that's what a lot of the discoveries happen, is what is going on. This is not behaving as expected. And then, because sometimes you get on a roll, you're on a train, yeah, we know how this works, we know how this works. Oh, wait a minute, what's going on here? That doesn't work at all. Why is that? And then you have to take a step back. Usually, 99.99% of the time, it was something simple. But every once in a while, it's like, holy cow, there's something new here. And so when that happens, there's a possibility of something new. But generally, you don't want it. So it's both, it's like Abraxas. You know Abraxas? Damien by Hermann Hesse. Abraxas, he was both, it's a being, he's both devil and God. He's both a benevolent, he's both God and the devil at the same time. So those kinds of things are like Abraxas. They're the devil because they could destroy an experiment if they're not behaving. But there can also be the light because in that unexpected behavior you may have discovered something. And that's where a lot of discovery happens. You're super connected. I mean, you could just, every year, somebody wins a Nobel Prize based on that. Something that they didn't think was supposed to happen, happened. And then they have to try to figure out what the problem is.
Really deviates away from your expectations. So the big one recent was Atlas and
The
CMS, the
750.
750 GeV thing. We've got this plot. We're expecting such and such to look like one way, and then we get this giant bump in it, completely different from what you'd expect, and it created 300 papers to be published within like 3 months.
Right.
And so you can give an artist some stuff whereby they go away, they say, okay, all you have to do is draw 2 lines and just make the 2 lines differ from one another at one point, and then give that to a theorist, and they can, just based on how those 2 lines are not fully overlapping, invent a physics theory to explain why.
Oh yeah, that's the other part. Theorists and there's scientists. There's a couple of different kinds of scientists. Countably finite, 2 or 3. Experimentalists are one kind, very much like engineers. A lot of engineering involved. But then there's theorists, and those are dreamers, guys like David. Like he said, you give David a line and a squiggly line, and he'll say, "Tell me what that means." And then it's the job of the theorist to dream up some idea.
Well, we always say that the experiments are to constrain the fertile imagination
Yeah,
of
exactly.
theorists.
Exactly. The theorists are going all over the map, and it's like, whoa, wait a minute,
explanations.
this can't be right, that can't be right, that can't. So we're trying to. So there's, and then there's phenomenologists, which are slightly kind of halfway between. Well, they look at. It's more about the interpretation of the data and how to get meaning out of data. Getting meaning out of data is not trivial. What was that?
It's not trivial.
It's not trivial. It's certainly not trivial. So you have all this data, right?
Yeah.
And you got to remember, in experimental physics, there are only a few things that you can do. You can generate flashes of electricity, flashes of light. What else do we do? Basically light and electricity, and we turn that into information. So position information, energy information, how things are curving.
Vibration, maybe. But that still becomes electricity later.
Yeah, it becomes electricity. There's only a really small number of things that we can use, techniques, physical processes that we can use to acquire any kind of data. Now, once you got that data, then how to interpret it is a whole different thing. You know, there's the simple thing of getting those dots and turning them into curves so that you can identify it as a pion or a muon or whatever. And then even when you get that kind of, so how can you get what are called observables? What observables can you construct out of your data, which are be useful to shed light on the problem? And it's not a trivial task by any means. They've got hundreds or thousands of guys on LHC trying to figure out, these analysis techniques to boosted decision trees and all of these things of how to get from the raw data, your raw data, to some kind of meaning. And then once you've got there, then there's a whole other problem of taking that and then trying to figure out what happened. What does this mean? And then once you've got that, then you got to hand it over to the theorists, and then the theorists saying, "Oh, okay, well, let me try to describe what is going on here. This could be in keeping with our, current theory. It might be an opportunity to inject something new." These protagonists and these relays happen even within the scientific collaboration all the time. It's continuous, right?
So if you wanted to take that, one of the ways I was suggesting we could do this was effectively you could make the artist or the art data, which is then given to the experimentalists and the theorists who have to make interpretations and make future experiments, which then results in more data, which you then continue the feedback loop. So you could do some interesting patterns there.
The aspect of data, that's what Tim, when we were
Description for that in English, but we can try to come up with a proximity. But if you're reading a novel and it's a certain translation, they might, that translator might have interpreted this word differently, and you get a different meaning, or maybe what the author had a pun or something, and that's lost in the original. So then you have a footnote that says this is actually really funny, but you don't, it's not coming across or whatever. So I guess because
if we acknowledge that we will have those translations.
Right.
Okay, but actually, just a comment. In a lot of places in science, I can say especially in physics, there are cases where you have the same physical system, and you have different descriptions of the same thing. And depending on what you want to do, sometimes one description is easier to use than another. But in this case, they are completely equivalent.
Yeah.
These two different descriptions of the same physical. So you have one physical system, but depending on what you want to do, sometimes one description is much easier to use than another one. Although this is the case where the descriptions are completely equivalent.
Would be something like, for example, the light can be a wave. Or like depending on what you're talking about, and you look at it.
That's a particularly challenging one.
Yeah, maybe
like wave duality. Particle wave duality.
But if you're trying to describe the motion, there are some cases where the wave equation is going to, your solutions will just fall out. And if you try to treat it like a particle, then it's, you get these massive equations. Like, I suppose it's theoretically possible, but when you're first being taught it, you're like, oh, this is the way that you do it. And that's because I always hated that in math or physics. You would learn this trick, and it's like, oh, well, everything just falls out when you have the trick. And it's like, well, it's because people have done this problem before, and they've found, this elegant solution to it. And so once you learn that, then that's sort of what the problem evolves into.
Can I propose a 1 minute sandwich break?
To the astronomers, that's good.
I mean, I'm not quite sure what I would say.
He said that astronomers wanted to wonder what else could it possibly be? Because these things
Sort of.
I don't think so.
In some ways.